Okay. Let's go way too. I can't go away. So now, true performance of a system is truly really based on the testing set. Although the performance during the test training of the system is valuable, the true test is measured by the testing set. Now, as novice in training and learning techniques, they obsess too much over the training set. And in training set, they push to 90% success in learning, then they go to 95% success, they go to 98%, 99%. At one point, obsessing over that marginal improvement with the training set, in fact, may harm you when it comes to the testing set. And based on a concept that I'm going to discuss in the next slide, no longer generalizing. You're putting it so far that it is memorizing every one of the training patterns. Therefore, it has no idea and it acts erratically when the testing set is presented. So this is the idea of memorization versus generalization. The two are somewhat intuitive in their definition. So memory is where the system has learned to memorize patterns and responds properly only to the patterns that it has seen during its training. It has no ability to infer, to extrapolate. It only responds to the patterns that it has seen during the training. Its response to any kind of a pattern that it has not seen can be very erratic. To go over the items that I have here, the system focuses on the specifics of the training pattern, learns the exact patterns and commits them into memory, into its memory of whatever sort it may be. It doesn't mean that the system is not really useful. You can, under some circumstances, come up with machine learning techniques that are useful under the operational mode of memorization. So, for example, the systems that we use in our computers are they record patterns, and based on those patterns, act. So the information that we record on your computers, they are recorded, memorized, if you would like to use that word now. They are recorded and memorized on the hard drive. From there, they go into the local memory of the computer, and then from there, they go to CPUs, and certain actions performed on the contents of the memory, and then stored back in the memory, and from there back to the hard drive. So in context, it is very useful. The only problem and the susceptibility of that model becomes that if your data is corrupt, the system cannot operate at all. So I'm sure you have seen the blue screen of death on these platforms, where if because you have some corrupted data in your hard drive, or you have some elements of memory that are corrupt, the system doesn't know how to handle missing there, it just crashes. Where I want to borrow some of the capabilities that human brain has, and that's called associative memory in humans. That I gave, and we have almost all of us have experienced this, where you sit there and you try to recall a person's memory or something, and you just can't seem to remember it. Up until that, there are triggers that may kind of come from memory. The lost information about the person's name suddenly becomes available because you smell something that might remind you of that person, or maybe you may hear a song that might remind you, and then suddenly the name of the person that was missing will be reconstructed. So the auto-associative memory, that based on some piece of information, the remainder of the information is reconstructed. Now, this kind of technique actually developed on the example that I gave you, on hard drives that, for whatever reason, regions of it are subjected to damage and information is lost. A system that's capable of memorizing can potentially recover the information that's missing based on the previous information. Most of the times, more than 95% of times, to my experience, people are more interested in generalization rather than memorization. We want to present some example instances, and we want the system to generalize and be able to handle situations that it has not seen before. So the that I produced yesterday is I'm sure I personally do not have the knowledge of every single type of car that exists in the world. But I am sure, based on my exposure to the that I have seen in my US, I will be able to identify a car, whether it's in Australia, somewhere remote in the world that I have never seen it before. I should still be able to identify it as a car. And that's my ability to generalize. I have developed a general understanding of what a car has an engine. It's used it has a form of locomotion. It has a cabin that carries passenger. It has a mechanism of steering. You may find a car that has 3 wheels, but we will be able to recognize it as a car. And this ability is called generalization, and it becomes the cornerstone of all machine learning techniques. We want to develop instances of machine learning that can recognize a person's face. It is achievable, and it is just impossible for us to go and record images of every person's face on this planet, and a computer essentially uses it to be able to regurgitate individual people. But what we want to be able to, maybe based on a population of 1,000 people, to develop a machine learning technique that can identify people's faces, and for be able to count the number of people in an image that has maybe, 500 faces on it. So we were really interested in generalization. For that, we are really interested because we want to prevent the system, either the system from memorization or steering the system towards memorization. That's where all of that comes in to how you actually partition your training and your testing data. If you're testing some variations of your training data, then you will force your machine learning technique to steer towards memorization. If your test data is very much different than training data, then your system is going to be forced to memorize. So these two, whether how you partition your data into training and testing, is going to relate to how whether you want to develop a memorization mechanism or the generalization mechanism. Later, as that overtraining system may actually result in loss for a testing set under some circumstances. We'll come back to that one. First thing and the simplest machine learning techniques that I want to cover today is k-nearest neighbor, and I'm going to demonstrate k-nearest neighbor as one of the items that is actually there in the app of the MATLAB, so we can easily demonstrate this. So I'm going to go through the theory behind it, and at some point I'm going to move on to MATLAB and show you how one can deploy the network and use it. So let's see, are there any questions? Alex and Hua. And I don't have any questions, but if there are any questions, please go ahead and post them now, or okay. Alex, any? Okay. All right. Sorry. K-nearest neighbor machine learning is one of the simplest techniques that you can put together. Minimize these. So nearest neighbors is so simple that it literally does not have a training algorithm, and its algorithm generally goes as follows. You don't do it during training, so it's only during testing. For any in order to establish classification, you query the nearest neighbors that are in your vicinity, in the vicinity of that unknown pattern, and there develop a consensus of what your classification should be. A very simple example would be, and I'm going to switch into the data and we can then I can do how it works. It had literally, again, no training. The supervisor, the person who is in charge of training the system, really you need to worry about two parameters. One of them, K, or the number of nearest neighbors that you want to query, whether you should ask neighbors or you should ask 100 nearest neighbors. That's the element to actually parameter that you want to worry about. And the second is a metric of distance. When we say nearest, near in what sense? And in the very clear and intuitive sense of what that should be, but as you need to think about it, the metric of distance not be as intuitively as we thought it was going to be. So for actually a large number of distance metrics out there that one can deploy, and some of them are going to perform far better than the others. And I'm going to conclude this talk by focusing on some of those. So, based on the information that I have presented here, one can ask the question of, is k-nearest neighbor for unsupervised learning mechanism? And the unsupervised, and back to really the algorithm, when you are querying your k-nearest neighbors, those nearest neighbors need to have their classification assigned to, they need to know whether they belong to class 1 or 2 or class blue or red. Are they male or female? They need to do that, and that knowledge comes from the supervisor that has reviewed all the data and has assigned them class red or blue. However, the part that's kind of interesting about k-nearest neighbor is related to whether it is used for classification or for prediction. The answer is that both, and I will comment on each of those briefly, and I'm hoping that's just going to be clear. It can be classification in the sense your unknown pattern can query all of the nearest neighbors and say, let me know if you belong to class red or blue. And let's say of the 11 nearest neighbors, 7 say we belong to class red, and remaining 4 say we belong to class blue. And for the unknown pattern may then decide, the consensus says I belong to class red, so therefore I belong to class red. And that becomes classification. In prediction, remember, in prediction, you produce a continuous numerical value. An example could be that I may want to predict a person's height based on shoe size and their weight. So given shoe size and weight, I want to predict a person's height. Now, this is a real number that may span anywhere from like 4 feet to 7 feet, or from 1 meter to 2 meters in height. Now, for prediction, k-nearest can be deployed by saying, okay, for an unknown pattern of my nearest neighbors, please tell me what is your height. And the k indications of height, and based on nearest neighbors, you can produce a value that would estimate your height. Now, how you produce that is an issue separate than the k-nearest neighbor, almost likely. If you have a height prediction of your k-nearest neighbors, whether you select a mean, minimum, maximum, average, median, whether a linear regression fit, that it still kind of stays, and a second thing to resolve. But still, you can use it somehow to perform prediction. Based on this, I'm going to stop at this point and answer any questions. If not, I'm going to switch into lab and go over the data set that I have distributed, and I'll ask you guys about that. At this point, let's focus. Neighbor, do you have any questions related to the theory and related to to the concepts that I have presented. Jenny, Alex, I have muted all of you. So if you have a question, please unmute yourself and ask. Otherwise, you can post if you have questions or not. Okay, so I'm going to assume no. All right. I'm going to I have posted all the examples that I'm working with today on the invitation with invitation that went out for yesterday and for today. They're all there. I don't know if I've received the job that I have also sent a separate email to everybody. They're going to appear in some aggregated form, tar, zip, somewhere, but they are there in the email and the invitation. So if you can go on, get them to follow with me, let me know. I'm just going to do these, assuming that you're watching, and you're watching and you're not following up. I'm going to do it at that pace. If you want me to slow down, just let me know. Genua, did you not receive my email? Let's see, checking this. I don't know if you can see my screen. Here I have the email that I sent to everybody. Let me see them. Jenny, in the chat, can you type in your email address? I'll just forward this to you. Alex, if you email address, I can send it to you too. Okay, to you, let me know. Please confirm got it. Did you want me to wait for you to, are you working along with me or should you present it and move forward? Okay. So here's my load example one. Repeat a little bit of the first session since you know that these are new to everybody here. I load data. My data was plotted. I have class 1, I have class 2. I aggregated both of them into my data set, and data sets, each one is 1,000 points. So my data in data set is 2,000 points because it's concatenated C1, C2. C2 have two features, X and Y, and they have a third column is their classification designation, and their classification is for the first points, after the 1,000th point, it becomes 2s, indicating points 1,001 through 2,000 belong to class 2. Now, this was also something that I covered in the first workshop. I'll just quickly comment that. I'm using MATLAB. These are available in R and Python, and many of the other common platforms. You can do it in C++, you can do it in Perl. So there are a variety of platforms available. I use MATLAB primarily because, as you can see, I go through this, I can do it with click point and click kind of an approach, and give us syntax dependence and knowledge of R or Python. The very thing I want to do when I come across something like this, I may want to plot things. There are ways you can plot things in MATLAB. By the way, MATLAB is a commercial software. It's costly to get, but for all affiliates of USC, it's free. And I suspect the same sort of free licensing is in place for academic environments. For $99, and there is an open source equivalent of it called Octave, but it doesn't have all the bells and whistles of MATLAB. So for now, I just made it simple to go through MATLAB. Once you grasp the concept, you can almost implement it in R, which we also covered in the past. The concept. Now, I wish the screen somehow. Put it right over here. Thing that I may want to do just C1, C2 with relation to each other to see what do they even look like. So I can highlight C1. Even though you can do this through command line, I'm going to do it through point and click. I click scatter plot. Get a plot of all the elements of C1. Command will keep this plot, and therefore anything else that I plot will be plotted, added to this figure, not a new one will be created. So I'm going to click C2, click scatter. This is my plot. Class 1 is in blue, class red. They are clearly separated from one another. Now, because I have history of visualization, I can see that this is a very simple case. They are very easily separated from each other. All critical thing to know is that all machine learning techniques will focus on a boundary. It's called decision boundary that will separate the two classes from each other. That's what I can do. I can separate them by drawing a line. This is one decision boundary where you're to the left of your red, you're to the your blue, no, to the right of red, to the left of it your blue. You can draw a decision boundary, a horizontal line that is above it your red, if you're below it your blue. The luxury of drawing a diagonal one, that if you are above to the right, you're red, below to the left, you're blue. So the solution is infinite. You can do horizontal, you can do diagonal. And there's a point to this, I'll come to it later. Now, but you want to go ahead and trigger classification learner. Once the mechanism is in place, okay, your new session, you want to load data from your workspace. Select the data object, which contains 3 columns. The first columns are my features, and my column is what MATLAB calls the response. You can call it the observation, you can call it classification. So this is the output of my network. The first columns are the inputs to my machine learning technique. Let's start a session. Now you can deploy all tools that are here. So you can do discriminant analysis, you can do logistic regression, you can do a neighbor. So I want to do a quick demonstration of binary decision tree, and I'm going to also do k-nearest neighbor. So in this particular case, I'm going to select a coarse tree because the decisions that I need to make are complicated. Well, then I can train my system. System is going to be a training, and 100% success in training my network. This is not given the simplicity of the data set. I can export my model You give it a name. I have already done this. You can say A, and then this trained model, I'm going to put it away now, will appear in your workspace. In the previous exercise I did DT. I may want to look at the rules that the binary decision tree has put together for me. DT is an object. If you DT has objects inside of it. Each objects have additional embedded objects. I am interested in the classification. So dot classification. Just do this. You'll get basically an if statement. You get a sequence of else statements that you can use in order to decide whether your system, how the decision tree is made. This is if you want to actually build a code around it. You may be interested in visualizing it, in which you can say it should be graph and following, where you look at column 1 and you establish a threshold of 5.1. So that may in fact be what I sort of put together. So 5.10 may be this line. If you're less than it, so you're on dead of it, you're class blue, class 1. If you're above it, right-hand side, you belong to class 2 or red. Decision time. So realizing that it is so simple in this case. To deploy nearest neighbor, you can go back in here and say, just give me a again, because it is fairly straightforward. I explain what course, find, all that stuff is in a little bit when I encounter problems. So nearest neighbor, you can then train your network. Nearest network. Remember, I made the claim nearest network does not have any training associated with it. So you ask the question of what is this training? This training really is what it's still testing every one of the decision elements of the data set to see how it adheres to on the k-nearest neighbor. So based on k-nearest neighbors, every single one of these points will be properly classified. So I'm going to ask the question to see if there are any questions. If not, I'm going to load the next data set, which is a little bit more challenging. And after the second one, I load the third one that becomes even increasingly more challenging. So are there any questions I can possibly answer at this point? Alex, I don't see any from you. Are you a spy? All right. I'm going to continue. This set, I'm going to space example 2. This, not sure what this is. In here also, again, I have classed the same exercise as before, except I have modified the data to be a little bit more challenging. So plot them. I'm going to class 2. I need almost the same data set as before. Now they have moved closer to each other. Now, this particular data set is very close to the other one. Now, tree is saying in column 1, if you're left of it, something happens. On the right of it, something happens. In column 2, if you're above some threshold, something happens. Below some threshold, something happens. Basically indicating, that decision tree, the way that it establishes its decision boundaries is all vertical lines. You see that if I was to draw a vertical here, that successfully creates my blue cluster. This is about as complete as I could do to be correct in applying all my blue, but take a loss of assigning all of these red dots on the left side of the line as class blue and not class red. The same phenomenon happens if I draw horizontal lines. So the moral of the story is there is a right line that will clearly separate data. And the question becomes, how does a binary decision tree handle situations like this? And remember, you only can draw column 1 above below, column 2 above below, which means pick one translates whether something can be on the left side, right side, upside, up or below. Decision boundaries are going to be vertical or horizontal only. They cannot be diagonal. So it's on a binary decision tree. So I'm going to start the app again. New session. I'm going to select the data again. Is exactly the same principle as before. I can subject it to the decision tree. You can see that first two things. On 4, it was not successful in assigning to individual clusters successfully 100% of the time. It was only 99.7% of the time. The blue should be red. These red should be blue. All the things that are marked in crosses are the ones that are misclassified. Now, also something I introduced last time is useful to look at it. Although this 99.7% accuracy is one, you can look at the performance of the system. There's selectivity, there's sensitivity, there's a number of other ways that you can quantify the properties of them. In learning opinion, the most complete one is the confusion table. That says out of 1,000 instances of class 1, 4 of them were classified as class 2. And 996 were successfully sent to class 1, 4 were misclassified. Class 2, 998 were correctly misclassified. 2 of them were classified as class, 4 of them were classified as class 1. So exact breakup as where are positives, where are the false negatives, and it gives you the complete picture. Now, so we're going to make the first one is that so this binary decision tree is not successful in completely separating the two, but then the second point is it's not doing as poorly as what I illustrated to be here. Based on what it seems we take large number of red misclassifications either in that region or in this region. You could say it's probably because it's maybe making this kind of a decision. But then the question is classifications here. So if you look at data, if you move these two lines up and down, you are not going to be able to reproduce this kind of a misclassification, these total 6. I can then capture the thing I have done already is this DT. And then I want to review, well, what did you exactly do? Which becomes that same. It has cleverly come up with a more complex decision tree that if it was plotted with following. In column 1, a score threshold of 2.7. So it's approximately here. If you side of it, you engage here, that would be on the left side of the data of the graph. If you're on the right of it here, you do additional one. So then based on column 2, it starts a fold at 7. So the about here. So on the right-hand side of this column, of this particular separator, which gets past the first decision point, if you are below this threshold 0.75, then you belong to one class, so otherwise you belong to. So essentially, it breaks the entire space into quartiles, and from there makes a decision. And you can, by doing this kind of a decision, now it can actually do better. I discussed this in more detail in the first session, so I'm going to labor over it too much when I get to k-nearest neighbor. So once I publish the first session, you'll see a little bit more. So let me get past this and get to k-nearest neighbor. In this instance, what I'm going to do, I'm going to create a second classifier by using k-nearest neighbor. Nearest neighbor, I'm going to train it. And you can see neighbor is more successful in classifying. It's classified everything correctly. Because essentially, if it was to isolate this particular point of difficulty and query around it, it would produce the appropriate selection. Basically, what it is really doing, now k-neighbor becomes a little bit more sophisticated in its operation. By saying any of these points have more neighboring that belong to one class, I'm going to assign myself to that one. It's not right, but conceptually, you could think that it is really placing a circle. It's taking an entire object and classify that as a class 1. Sort of. So I adjust the proper size of the circle. I say the thing with the blue line. So k-neighbor actually kind of performs better than the binary division tree. The points that I was talking about, there are 2 parameters when it comes to neighbor, and those are in the advanced options. Number of neighbors is k. In this particular case, the default is 100. And distance. And the distance, here are a list of distances that that one could potentially select, and this one was the Euclidean distance. So I decide as well, and I'm going to load the third one, the third bit that may be more challenging. And then this is going to go straight to the app, and I'm not going to plot things. And it's as simple as before. You can see data are far more complex now. They are kind of like, you can still draw a line. You can't have a clear vertical horizontal line like before, like examples 1 and 2, that maybe with a few lines you can separate things. You have to draw a diagonal line here. So if I was to deploy a binary decision tree and just basically on the train set, you get 96.6% success, 96.5%, and you can see that these are the points of contention. If I create k-nearest neighbor, and have some issues with k-nearest neighbors, if I was to now play around some of the parameters, such as not the Euclidean, but Mahalanobis distance, and I'm going to explain what these are a little bit later. You can train it 0% success. This was a case of nearest neighbor with the distance being declared Euclidean distance. This is the case of exact same thing where the distinction being the measure of distance is Mahalanobis distance. So just tinkering a little bit with the parameter sets, you can actually achieve much better success. And again, query to see if there are any questions. If not, I'm going to move to k-means clustering. So, Brendan, do you have a question here by any chance? Feel free to ask questions. Okay, so continue with my presentation here. Nearest neighbor, the reason that I'm showing you k-means string is because oftentimes they are mistaken for each other, and I just want that distinction from each other. So nearest neighbor, you just simply select your k-nearest neighbors, and you sense of classification or prediction, and you move forward. K is a little bit more sophisticated, and it lends itself for different applications. So you can do parametric or non-parametric. I haven't discussed what that means, so I have put in here. If you know what it means, you will know what it means. If you don't, just get past it. To deploy it in a parametric sense, meaning that when I deploy k-means clustering, you have to know how many classes are there. So when I like to have patients not responders, and I want to do k-means clustering, I know there are two non-responders. And the examples that I'm doing, I know there are two clusters. They are red. And the algorithm for n clusters goes as follows. So the algorithm is by selecting n random representatives for the centers of each cluster. You pick random points, centroids of each one of the clusters. You assign from all remaining data points, you put a distance. How close are you to each one of those centroids? Which is the closest to you, you can establish the membership of the unknown data or the training data to that cluster that's represented by the centroid. But at any given point, you make n distances for every given point. The one closest to you, the point become a member of that cluster. Now, once you've gone through all of your data points and you have assigned them to their appropriate cluster, then you calculate a new centroid based on membership. So in the case of, I have 2,000 data points, 1,200 to one cluster, 800 to the other cluster. On the basis of their population, you'll calculate an average rate. And you have centroids are modified, you repeat the whole process. You establish a new membership because now the sites are different. Repeat the process. Oh, there is no update in some membership of the points, or if you achieve a maximum iteration. You have a collection of members that oscillate between class 1 and class 2, and in that instance, you want to bring the oscillation to a termination by putting a maximum iterations. Supervised learning or unsupervised learning. So when I said there are two clusters of data in your data sets, well, which one of the data belong to class 1 or class 2? So it's up to the algorithm to establish the membership. In that sense, it is unsupervised. You can either, you can also still work with it in the context of supervised. So in this particular case, again, distance, a measure of distance is critical. You need to know what distance to choose. I'm sorry? That is correct. So you have to, as a trainer, you actually decide which one is better. And usually the process goes, unless there's a particular information that you are incorporating into your, of the data, allude you as to what kind of a distance matrix you should be using. Okay, but in general, you kind of try different metrics and see which one works best based on your training testing site. Things that I want to show are Euclidean, Mahalanobis, and block distance. We're going to run out of time. I don't want to extend this. I'll explain each one of these in detail next time. But I'm going to go back to my examples here. I want to select my goal 2. Clear my 2. So Matplotlib have k-means clustering, but it is not part of its app. So what I have created a k-means cluster sequence commands that perform the work for you on your data. So jumping over it, figure simply produces, let me just perform these commands. Selection. So I guess so figure will generate a figure for you. Hold stops it. Make cluster and scattering plot of both data sets. And there, in means clustering, where you give it the data. So I send 2 dimensions, 2 variables, and this is the enough clusters that it needs to produce. That's 2. So, and there, it returns the indices membership. So my data has 2,000 points. For every one of the points, returns the point number 1 belongs to class 1, class 2. And you can see they're pretty much all for 1,000 points of class number 2, and that's class number 1. And it's because it is displaying the class members, it's arbitrarily selecting the first set to be class 2, the second set to be class 1. Returns the index and returns the center of each one of the clusters, what's shown in black X's. In here, I plot my data where I plot only the data that has an index of 1, the first column, second column, and I mark them as red dots, so that's this one. And on again, I plot data for index 2, and I'll show them with the green dots. That would be this one. So I'll plot them, and this particular, the second to last plots the X's with distinct marks, and in the title, just as a title there, just if you want to know how it is. So you see, let me see if it zoom in. Oh, I didn't do it. I'm gonna. Produces, and you can see, you'll be able to make out. So some of these points are red, correctly classified, but these points are green. Really belong to class red, but they are misclassified as class green. And these points that it just seems like they should clearly be classified to class green, they're actually classified to class red. And this is because my measure of distance is which is inappropriate for this data set. So what I'm going to do, I'm going to see if I have any questions. But in the workshop tomorrow, I'm going to start with this define the metrics, expand on them a little bit more, and run this one with a couple of other examples. And we'll probably take out a third of a session, and then I'm going to start with neural networks. Are there any questions at this point? I'll try to aggregate these someplace. If you data any of the scripts sooner than I'm producing, just email me and I will send it to you by email. But it would be advisable for you guys to actually repeat this process on your own. It's fairly straightforward to tinker classifiers in MATLAB, and that's the appeal of it, to just become familiar. I post the first from Monday, which was yesterday. We had technical difficulties, so that one didn't materialize. today was almost like a repeat of it. So, I will post first one. And it takes really 2 days for me to get WebEx content and convert it to a format that can be posted. So I will post it as soon as I can. Questions, I'm going to conclude at this point, hoping that I'll see you tomorrow. I see folks tomorrow. Bye.